So one of the things that made derivatives more challenging for functions of several variables than they do for functions of a single variable, among other things, is the fact that limits in multivariable functions exist from infinitely many different directions as we approach a point, as well as infinitely many different ways to approach that point. And so we needed a vector quantity to represent the derivative, the gradient vector, because it was able to package all of the directional derivative information, all the slopes of the graph of a multivariable function in a single entity, right? A single vector quantity called the gradient. And so, as you might expect, integrals in multivariable calculus likewise are made more challenging primarily by the fact that the domain of our multivariable functions is at least a two-dimensional, a region in a two-dimensional space, rather than in single variable calculus where it's just a region in one-dimensional space, which we can think of as something simple like an interval on the real line, right? And so, for example, when you define the definite integral of a function in single variable calculus, you say, we're going to take the definite integral of this function from x equals a to x equals b, because the domain of integration is just an interval, a little chunk of the real line. And all you need to define an interval is a left-hand endpoint and a right-hand endpoint, which are both numbers. But of course, if I have a function of two variables whose domain is some subset of the xy plane, if I want to do a definite integral of a multivariable function, I have to specify some subset, some region of the xy plane that is going to be our domain of integration. And the problem is that that region can look however we like it to look, right? It could be a solid rectangle. It could be a filled-in circle. It could be some sector. It could be like the region trapped in between a parabola and a hyperbola in between. So the biggest challenge, I think, that we're going to find when it comes to integrals of multivariable functions is just the process of describing what is the domain of integration. That's the good news. It's the bad news. It's also the good news, is that once we actually get to the calculus part of integration in multivariable contexts, the calculus part is going to be familiar. Just like the partial derivatives in our last chapter were pretty easy to pick up on because they were just ordinary derivatives, but we had to pretend that some of the variables were constants, right? It's going to be the same thing with multivariable integrals. We'll be able to do multivariable integrals through a process of applying the ordinary single variable fundamental theorem of calculus. Find an antiderivative, evaluate it at the upper limit and the lower limit, and subtract the results, right? So that same familiar fundamental theorem of calculus definite integration process from Calc 1 and 2 comes back and helps us again in multivariable calculus. And so all of the legwork gets invested into just describing what is the region of integration and what do we do with that description as part of the integral process. So again, because we have a shortened semester, all of the exposition that the authors do about definite integrals is some of it's going to be abbreviated. So the entire first section of chapter 11 on multiple integrals is a section where the authors walk us through the Riemann sum definition for double integrals. So double integrals is where we're going to begin. Those are going to be integrals of functions of two variables, f of x and y. And so they walk through the Riemann sum definition. How do I divide up a domain of integration and set up a sum of volumes of rectangular prisms that then, as we refine that partition and let the lengths and widths of each of those little tiny rectangles go to zero, it approximates the volume underneath the graph, right? And so that's where the authors of our book begin, and there's a whole section on it, and we're going to bypass that whole section in the interest of time. But the most important thing to get out of that section, I think, is what is it that a double integral of a scalar function is actually measuring? It is measuring, just like in single variable calculus, it's measuring the amount of space underneath the graph of a function. And by space, in single variable calculus, we mean area, where areas above the x-axis in single variable count as positive, areas underneath the x-axis count as negative. Well, all we do is import that into 3 dimensions and replace area by volume. So the double integral of a function of two variables over a region in the xy plane is the volume underneath the graph that lies above that region in the xy plane, where volume that's above the xy plane itself counts as positive, and volume that's below the xy plane counts as negative. So it measures a signed volume underneath the graph of our function of two variables. So with that motivation in mind, and all of that motivation to put it onto rigorous foundation requires all these Riemann sums, et cetera, et cetera. With all of that motivation getting for us swept under the rug, the question is, how should we compute such a thing? Right? Where should the value of an integral of a function of two variables actually come from? And so the preview activity that I want to start us with is 11.2. And this activity asks us to think about the function f of x and y as 25 minus x squared minus y squared. So its graph is this upside down paraboloid, which goes up to 25 on the z-axis and then has circular cross sections. And so what we're going to walk through in this preview activity is a way of slicing up this volume that we're trying to find the volume of. It's almost like you're sort of putting it through a bread slicer. And that bread slicer is going to slice it perpendicular to the x-axis. And each of those slices perpendicular to the x-axis is going to have an area. And then we'll use a regular single variable integral to measure the area of each one of those slices after we've passed this through the bread slicer. Right? And so the idea is, if I can slice this perpendicular to the x-axis, so treating x like a constant, I'm going to get a slice whose area I can compute with an ordinary definite integral. Then I just have to add up the volumes of all of those slices after we give them little infinitesimal thicknesses delta x, let those delta x's go to 0, and we should get another integral that then adds up the total volume under the graph. So this is the basic strategy of how we'll be computing double integrals, is we're going to think of it like we're slicing our volume in one direction at a constant value of, let's say, x. And each of those slices has an area. We'll find the area as a function of x for each one of those individual slices. And then we just have to integrate those areas as a function of x in order to determine our total volume. And so at the end of the day, what we end up doing is computing the integral of an integral. So this process is called iterated integration. So to find the area of one of these slices, we end up doing an integral with respect to y, treating x like it's a constant. And then to get the total volume, we're going to use an integral to add up all those areas as functions of x. So integral with respect to y gives us the areas, and then the integral of that with respect to x is going to total up the volumes. So this preview activity just sort of takes us through the process of what that looks like. And I've done the last part for you, which is just the interpretation of how the Riemann sum that's suggested in question C turns into an integral. But let's have you take a few minutes with your group to look at parts A, B, and C, just to sort of fill in the details and maybe write a couple sentences that summarize this activity that I think probably I've given away most of the spoilers about in the last couple paragraphs that I said. So go ahead and do those A, B, and C parts, and then we'll be ready to move on and get some more practice. So you're sort of filling in the details here that are intended to make this idea of putting this volume underneath the graph through a bread slicer, intended to make those details more concrete, right? Make them more rigorous. And so what we're doing here is essentially saying, if I take a slice through this volume that has an area given by a of x, and a of x is, according to single variable calculus, the area under the graph of the single variable function f of x and y with respect to y, between y equals 4 and y equals minus 4, right? Because this f of x comma y, if x is treated like a constant, the graph of f of x comma y in yz space is the trace of the graph of our two variable function through the plane x equals constant, right? And so the integral of that trace is going to be the area underneath the graph of that trace in yz space. And then if we give that area a little amount of thickness, call it delta x, then multiplying that area by that thickness, area of the base times the height, gives us the volume of this prism. And that prism sort of stacks maybe underneath, maybe above, maybe a little bit of both, but it sort of approximates the volume underneath the graph of our function at that point, xi star is called here, right? And if I add up all of those volumes, then we're going to get an approximation to the total volume underneath the graph of this function, from x equals -3 to x equals +3. So all the different slices in the x direction. And then as we let the thickness of the slices go to 0, so we're getting more and more and more slices, each one of them is thinner and thinner, and so they're going to be a better and better approximation to the volume, that as long as my functions are integrable, so continuity is actually enough to guarantee that, then what ends up happening is that this converges to the volume underneath the graph. But when we read this activity from beginning to end, what it shows us is that the volume underneath the graph can be found by first finding this area function, and this area function is the integral of f of x and y with respect to y only, treating x like it's a constant. And so if I do that integral using like single variable calculus strategies, what it's going to spit out is not going to have a y in it anymore, but it's probably still going to have x's in it, right? Because we treated x like it was a constant. And when we evaluated the limits of integration using the fundamental theorem of calculus, we would have plugged in values for y, which were numbers. But x, we haven't plugged in anything for, so x is still going to come out of this because the area is a function of x. My different slices have different amounts of area. And then we take that function of x and find its integral from x equals minus 3 to 3, and then that's going to pop out the volume. So an iterated integral, double integrals are computed most often by taking an integral of an integral, where at each step we're treating one of the variables as though it's the variable, and all the other variables at that step are being treated as though they're constants. I'm in the habit usually when I do multiple integrals, especially as we're just getting our feet underneath us, of putting the variable name in the limits of integration of each one. So instead of just writing minus 4 to 4 and minus 3 to 3, I've written here y equals minus 4 to y equals 4, just as a reminder. Because if we were to evaluate this integral, let's actually do that just for kicks, right? So according to the fundamental theorem of calculus, if I do that integral that's in the middle, this is the integral from y equals minus 4 to y equals positive 4 of f of x and y, and f of x and y in this problem is 25 minus x squared minus y squared. And I want to integrate that with respect to y. So I want to treat y as though it's the variable, and I'm going to treat x in this process when I do the first integral on the inside as though it's a constant. So according to the fundamental theorem of calculus, I need an antiderivative for 25 minus x squared minus y squared, where y is being treated like the variable, but x is being treated like a constant. So what would an antiderivative for 25 minus x squared minus y squared look like in that case? So just like with partial derivatives, we take antiderivatives here by suspending our belief that x is a variable, treating x like a constant and treating y like it's the variable. So the antiderivative of 25 with respect to y is going to give me 25 times y. The antiderivative of x squared with respect to y gives me x squared times y, because that x squared is also being treated like it's a constant coefficient here. And it's only the y squared that transforms into a y cubed over 3 as part of this process. So there's my antiderivative with respect to y. And so now my job is going to be to evaluate this quantity from y equals negative 4 to y equals 4. So let's put that in some brackets, and y equals minus 4, and evaluate at a subscript of y equals positive 4. Okay, so I'll plug a 4 in for y, I'll plug a negative 4 in for y, and in the process I'll get, so let me go down to another line here. Let's see, so, oops, my bracket ended up in the wrong place. I want to make sure I'm not, not screwing anything up here. There we go. All right, so at y equals 4, we're going to get 100 minus 4x squared minus 1/3 of 4 cubed, and 4 cubed is 64, so minus 64 over 3. I'm just going to do a little bit of talking out loud arithmetic here. So 100 minus 4x squared minus 64/3. So there's my evaluation at y equals positive 4. And then at y equals negative 4, we're going to get negative 100 plus 4x squared, and then minus 1/3 of negative 64, so plus 64/3. So actually it's kind of a interesting to note here that this function as a function of y is actually an even function. And so the value of its antiderivative at 4 and the value of its antiderivative at -4 are equal and opposite. So what we end up getting is just twice the value that we would have gotten if we did y equals 0 to 4. So I'll finish this all out. This is going to give me 200 minus 8x squared minus 128 thirds. So that's my area function, right? As a function of x, each of the slices that we get in the process has that area, 200 minus 8x squared minus 128 thirds. And so now, to get the volume, we have to integrate that as a function of x from x equals -3 to x equals +3. So the integral from x equals -3 to x equals 3 of 200 minus 8x squared minus 128 thirds with respect to x. And now this just becomes your standard single variable calculus definite integration problem. Right? So notably, at the end of this process, we're going to end up with a number as our volume underneath the graph. And you'll notice that as you work an iterated integral from the inside out, each integral that you do is going to have one fewer variable in it at the end of each integration step. And so that's one way to kind of check your progress as you go along. 8 thirds x to the power 3 minus 128 over 3x. And then I'm going to take that and evaluate it from x equals -3 to x equals +3. And just like with the y function, this ends up being an even function. The integrand is an even function with respect to x, so I could just have integrated from 0 to 3 and multiplied the result by 2. If I do that, I'm going to get twice 600 minus 8 thirds times 3 cubed, and so that's going to be 72, minus 128 over 3 times x, so that's going to be 128. So actually, we end up not getting a too awful of an answer. At least our answer is a whole number. 600 minus 72 minus 128. That's going to give me 400 multiplied by 2, and that gives me 800 for the volume. Okay. As soon as that finishes being input there we have it. Looks like I might need to make it a little smaller to fit it. Cool. So that is what double integration is about, right? Is that we are trying to find the volume underneath a graph of a function of two variables that lies above some region in the xy plane. And in this particular example, that region was the region where x ranged from -3 to 3 and which y ranged from -4 to 4. So what is that region, actually? So the region that we just integrated over, right, that we found the volume underneath the graph of 25 minus x squared minus y squared over the region in the xy plane is the region where x went between -3 and 3. So it was described by having x coordinates that satisfy the inequality x is between -3 and +3. But it also satisfied that the y coordinates were between -4 and +4. And so the region over which we integrated, so that the domain of the xy plane that we computed this integral over was this rectangle, right? The rectangle bounded by the vertical lines x equals plus and minus 3 and the horizontal lines y equals plus and minus 4. And so I think the last thing that I want us to notice about this example before we move on to the next activities is that the limits of integration, both of my sets of limits of integration in this problem were constants, right? X equals -3, x equals +3, y equals -4, y equals +4. And because those limits of integration were constant, what shape do we have to get for our region of integration? If it's got to be bounded by a pair of vertical lines and a pair of horizontal lines, what must it be?
A rectangle?
It's got to be a rectangle. Yeah, there's no other option. And so rectangles are great I mean, we can use rectangles to approximate a lot of different other kind of weird shapes, but we want to be able to build our capacity to find integrals not just over rectangular regions, but also over regions that might not be rectangles. And so a region that might not be a rectangle might involve having limits of integration that are no longer just constants, that might involve some appearances of variables within our limits of integration. And so that is, I think, that's the big muscle that we have to work as we're starting to get used to double integrals, is how do I, given a region that I want to find an integral over, how do I find appropriate limits of integration to make sure that I'm describing the region that I'm trying to describe using inequalities that bound the variables. And so that's where we want to go next in this process.